All right. Okay, so let's it's week 6. It's week 6. Happy Monday. We'll get started here. All right, so let's take a look at the island hopping example again, island hopping. And so you know, this is the example we looked at Friday. We said we got an island chain. There's seven islands, and this politician, he wants to visit the islands proportional to their populations. And so in this island chain, kind of their the target distribution is going to be this: 1 over 28, 2 over 28, 3 over 28, all the way up to 720 over 28, because the islands are numbered 1 through 7, and their populations are proportional to their island number. So island 1 has a population of 1,000, island 7 has a population of 7,000, and basically a quarter of the island nation's population lives on island 7, whereas only 1/28 live on island 1. And so this is going to be our target distribution here. Okay, and this is the algorithm. This is how the politician decides where to go and where to move. Every morning, the politician flips a coin. If the coin lands heads, then he's going to propose the island to the west. If the coin lands tails, he proposes the island to the east. And he's going to he checks the population of the proposed island and the population of the current island. And if the proposed island has a higher population than the current island, he's going to go there. He definitely goes there, probability 100%. Okay. And if the proposed island has a smaller population than the current island, then he goes to that island probabilistically, right? And so his probability of moving to that island is going to be P move, which is the ratio between the proposed probability and the proposed probability divided by the current probability, right? And so we will move there with this probability, and to decide, he generates a random uniform value u. If u is less than or equal to p move, he's going to move to that proposed island. If not, he stays at the current island. Okay. And the system works, right? In the long run, the probability of the politician being on any one of the island matches the relative population of the island. Okay. And so what we did on Friday is we said, all right, well, if this is the system that he uses for moving, we can figure out this transition probability matrix. All right. And so we went through and we did each row, and we said, if you're currently at island 4, the probability of going to island 5 is 1/2. The probability of going down to island 3 is 3/8, and the probability of staying where you are is 1/8, and things like that. And we can go through and we can find the probabilities, the transition probabilities for every single island. And on Friday, we said, well, if this is your transition probability matrix, then the stationary distribution is the left eigenvector of this matrix. And we found the stationary distribution. And we also showed that the stationary distribution is equal to the target distribution. So that's what we did on Friday. We went through all of this. We figured out this transition probability matrix. We found the stationary distribution. We showed that stationary distribution times pi times p is equal to pi. You get the stationary distribution back. And we showed that pi, that stationary distribution, is equal to the target distribution, which is what we want. Okay. What we didn't actually do was we didn't actually run the Markov chain itself. Okay. And so that's what I'll do here. I wrote some code, and we're going to actually run the Markov chain. So we're going to kind of simulate the movement of the politician, bouncing from island to island. Okay. And so so this is what it will do. Okay. We're going to propose a value. We're going to propose an island, x proposed, and that's going to be the current island, either +1 or -1. Okay. We propose x at time t +1 with probability 0.5, and we propose x at time t. Our current island is x at time t -1, okay, with probability 0.5. So our x proposed can either be the current value x at time t +1 or x at time t -1. So this is what we've got. And based on that, we calculate the probability of moving, okay? The probability of moving is going to be P proposed divided by P current, okay? I have to throw in this min here because if the proposed location has a higher probability than their current location, P proposed divided by P current is greater than 1. And we know probabilities are bounded by 1. You're not allowed to have a probability that's greater than 1. So P move is going to be the minimum between 1 and whatever this this fraction is. Okay, so if the fraction is greater than 1, then P move is just equal to 1. This is a smaller value. And if this P proposed is smaller than 1, it's going to be whatever this or P proposed over P current is smaller than 1, it's going to be just whatever this fraction is. Okay, so it's basically this fraction, except when if the fraction goes bigger than 1, it's limited to 1. Okay, so and we're going to move there by sampling a random value u from the uniform 0, 1. If u is less than P move, then we move to the proposed island. X at time t plus 1 is going to be the proposed island. Okay. If u turns out to be greater than P move, okay, then we don't move and we stay put at the current island. And x at time t plus 1 is equal to our current value x at time t. Okay, we stay at the current island x at time t. Okay. All right, so I coded this up. I have a function called propose. Propose is a function, and it's a function based on the current value. And the value it returns is going to be current plus either 1 or minus 1. So I use sample to randomly pick either 1 or minus 1. So I do sample 1 or minus 1. So I say size 1, pick 1 or minus 1. And that's going to be the value it returns. It's going to be current plus 1 or current minus 1. Okay, and so that lines up with what we have here, right? So x proposed is going to be the current value plus 1 or minus 1. Okay, and over here, we have a function that's going to return the target probability, okay? It's going to return the target probability is x over 28, okay, if x is 1 through 7. So I'm going to say I have an if else. If x is one of the values 1 through 7, return x over 28. Okay, and for any other value, return 0. And so we can see that, this will give us back basically our target distribution. This is our target distribution. So if x is any one of these values, 1 through 7, which is kind of our location, return x over 20. That's going to be the probabilities there. All right, so our chain, I'm going to just run 1,000 iterations, 10 to the 3, 1,000 iterations of our chain. And I'm going to start the chain at location 4. That's just an arbitrary starting location. If we wanted to start the chain somewhere else, say location 1 or location 7, we could do that. It doesn't matter. Okay, and this is what each iteration looks like. At each iteration, I'm going to take my current location x at time t. So I'm running this loop from t equals 1 to 999. Okay, and so x at time 1, xt is going to be my current value. Okay, and then I use the propose function to take my current value and return a proposed value. So the proposed value is going to be either current plus 1 or current minus 1. And then we're going to calculate P move. P move is going to be P proposed, whatever this is, x over 28 divided by P current, also x over 28. Okay, so we're going to calculate this probability of moving, and then we're going to either move there or not. Okay, so I generate a random u from our uniform. I just get one random uniform value, and if u is less than P move, we'll move there. Okay, so technically P move is the minimum between 1 and P proposed divided by P current. Okay, but if P move ends up being greater than 1, then u is going to be true anyway, right? Like I don't actually have to say what is the minimum between 1 and P proposed over P current, because U is always going to be less than, like, if P move turns out to be 1.3, U is going to be less than 1.3 anyway. So I don't actually have to do the min. I could, but it's unnecessary. Okay, so if U is less than P move, we're going to accept the proposed value. So X at time T plus 1 becomes the proposed value. We're going to take the proposed value and store it into X at time T plus 1. Otherwise, we're going to take the current value and store it at X at time T plus 1. So X at time T plus 1 will just be the current value. Okay, and then and we just kind of iterate over and over and over as T goes from 1 through N minus 1. Okay, so at, you know, with N being 1,000, it'll end at 999, and it will either store the proposed or the current value into spot 1,000. All right, is that okay as far as running the code for the Markov chain? I just kind of want to make sure that what I've written here makes sense, and we can see that it's a direct translation of the algorithm, right? So here's the algorithm, and this is the Markov chain. Okay, let me go ahead and give you the quiz answer. Today's first quiz answer. First quiz answer is D. D as in dog. D as in dog is the first quiz answer for today. Okay, D. D as in dog. Hopefully you guys got that. All right, so so I run the Markov chain. It runs for 1,000 iterations, and let's just go ahead and count up the results. So I say, so we've taken X. X is a vector of length 1,000, and I say, all right, table up those results. All right, so those will be the counts, and just so I can compare the results with their kind of their expected probabilities, I'm going to take and turn everything into relative frequencies. So I do take my table of counts, and I'm going to divide by n, and I'm going to compare that to the target probabilities, which is basically 1 through 7 divided by 28. Okay, and so here's a kind of a table or a matrix comparing these results. Okay, so the empirical probabilities is, you know, out of 1,000 iterations, basically I got the number 1 28 times. Okay, so my empirical probability is 0.028, and according to, you know, the target distribution, we should get around 0.0357. Okay, I got the number 7. It should happen around 1/4 of the time. It happened to us around 267, a little over a quarter of the time. If I do a chi-squared test to say, you know, is there a significant difference between what we saw and what our target probabilities were, our p-value comes in at around 0.6, and so it says, you know, we got nothing to worry about here. Okay, so we see a very close alignment between the empirical probabilities and the target distribution. Okay, and the chi-squared goodness of fit test produces a large p-value, so we would say, you know, we don't have any evidence to say that the values generated by the Markov chain are not coming from the target distribution. Okay, so we got that. And here's kind of a bar plot showing the empirical versus the target probabilities. Okay, and we see fairly close alignment. This is not perfectly the same height. Okay, but we're getting something fairly close to each other. All right, so so that looks pretty good. Okay, and you know, our chi-squared test says, you know, this is the differences we're seeing is nothing to worry about here. All right, and here is kind of what the Markov chain looks like. Okay, and this is just the first 200 values of the Markov chain. And so, you know, I started off at 4, and I must have flipped tails because I proposed the value 5. The value 5 has a higher probability than the value 4, so we move there with 100% probability. Here I came here, and at 5 I proposed the next value. I got a 6, and so we went there with probability 100%. At 6, it looks like I must have flipped I proposed 5, but then I didn't go there because I got 6 and I got 6 again. So we can see kind of there's the 6 appears twice here. And then we proposed a 7 and we moved. We proposed a 6, we moved. We proposed a 7, we moved. And then at 7, it generated several values at 7. And so we don't know if that was instances where it proposed 6 and rejected it, or maybe it proposed 8 and rejected those as well. Okay, so so we're not moving over there. Okay, and so the chain kind of bounces around, and we're either moving up to the right or to the left, east or to the west. Okay, and then we end up down here. And so, you know, now we're generating values like 1 and at 1 we have a few iterations where it looks like we're proposing the value 0 and, you know, we're rejecting it. Because if I'm at 1 and I propose the value 2, I'm going to go there 100%. Okay, but it looks like if I flip the coin and it says, you know, go west to island 0, you know, we're going to just stay put at island 1. Okay, so that happens for a few iterations, and we kind of go back and forth, and this is kind of just what the Markov chain looks like. So the next value that we're generating, you know, is correlated, is related to the current location, but then in the long run, we get values that look like they come from the target distribution. Okay, so the values that this Markov chain generates looks like the target distribution, even though the values themselves are not IID. They're not independent of each other. They depend on the previous values here. All right, is that all right? Does that look okay with you guys? All right, so now I'm going to just say, well, what happens if we run the chain even longer? So I'm going to run this for 100,000 iterations, 10 to the 5, okay? And this time I just arbitrarily choose to start at 7. It doesn't matter. Okay, but anyway, I run basically the exact same code. You know, current value exit time t is the current, propose a new value based on the current value, find the probability of moving, and then if I move, take the current value and set it to exit time t plus 1. I mean, the proposed value, set it to exit time t plus 1. Otherwise, set the current value to exit time t plus 1. Okay, and then so I tally up my my counts, and this is the resulting table. We get a table of counts and relative probabilities. And if we look at this, so we're expecting the target is 0.25 and we're getting 0.245. So we're getting something pretty close. The target's 0.2143, we're getting 0.2107. So these probabilities, the empirical and the target distributions, seem to line up pretty well. Okay, they line up pretty closely. When I create a bar plot, we see these things line up very closely as well. All right. However, look what happens when I run the chi-squared test. I get a p-value that's very, very tiny. Okay, and this is one of the issues with the chi-squared test. The chi-squared test is very sensitive to sample size, and in general, if you're doing a chi-squared goodness of fit test, you know, you generally probably don't want samples much greater than, say, 2,000 or so. Okay, with large samples, the chi-squared test is going to detect even kind of the smallest of differences. And so, you know, when you have a sample of, say, 100,000, you can run into issues here. Okay, and so so in some of these cases, you know, it might make sense to use the p-value to be something much smaller than 5%. You know, maybe on the order of like 10 to the negative 10 or something like that. Okay, the discussion regarding this is a bit beyond the scope of the course, but you know, it's worth reading. There's a good kind of post on Stack Exchange that discusses this for, you know, a goodness of fit test when you have very large samples, and basically the summary is, if you have a very large sample size and your p-value ends up being very tiny, don't worry too much about it. Okay, I know in the homework assignments I have you use chi-squared tests, you know, quite a bit for these discrete distributions, but if you have a very large sample, it may or may not be the best test to use. Okay, and so in some cases you might be better served simply by comparing the empirical and theoretic probabilities, just kind of using your best judgment there. All right, so so if you have very large samples, again, kind of on the order of something greater than 2,000. Maybe the chi-squared test is not the best indicator there. All right, so let's talk about the Metropolis algorithm itself. Okay, so we've been doing kind of this little discrete island hopping example, and basically we can just kind of modify it a little bit, and we'll get the Metropolis algorithm. Okay, so for the Metropolis algorithm, we've got function f of x. Okay, f of x is a function that's proportional to the desired probability distribution p of x. Okay, so you have some desired target probability distribution p of x, and you need a function f of x that's proportional to it. And what we're going to do is we're going to just start at some arbitrary point x at time t to be the first sample in the Markov chain. So it's an arbitrary value. And then you also need an arbitrary proposal distribution. Okay, the arbitrary proposal distribution is going to be g of x, and this is going to be kind of, what does it propose given your current value? So given the current value x at time t, what value can you propose? For the Metropolis algorithm, the proposal distribution must be symmetric. On Friday, we'll take a look at the Metropolis Hastings algorithm, where the proposal distribution does not need to be symmetric. Okay, so the Metropolis Hastings algorithm proposal distribution doesn't need to be symmetric, but for the Metropolis algorithm, it does. And so, so that just means the probability of proposing xa if you're currently at xb is the same as the probability of proposing xb if you're currently at xa. Okay. Anyway, for each iteration, the way it works is you generate a proposed value, x proposed, based on your current value from the distribution g of x, given that you're at x at time t. Okay, and then you use the function f of x, which is proportional to the target distribution, to calculate the probability of moving. Okay, and so the probability of moving is the minimum between 1 and f of x proposed versus divided by f at your current value, x at time t. Okay, x, your current value. Okay, compare your proposed probability of the proposed location divided by the probability of the current location, or at least using a function that's proportional to it. And then you either accept or reject the proposed value. So you generate a random number u from the uniform distribution. If u is less than this p move, you accept it, and x at time t plus 1 is going to be x at is the proposed value. And if u is greater than p move, reject this candidate value, and you reuse the current value. Okay, so x at time t plus 1 is going to be the current value x at time t. Right, and so, one thing about the Metropolis algorithm is that the samples it produces, you might get values where the same value appears more than once, which will never happen if you're drawing random independent values, right? If you're drawing random independent values from a continuous distribution, what is the probability that you're going to generate the same exact value twice? Okay, that's probability 0. Okay, getting on a continuous distribution, the probability of getting the same exact value twice, has a probability of 0. Now, I guess technically on the computer, it's not 100% continuous. It's approximately, we're limited by floating points, so maybe not probability 0, but something close to it. Okay, but here with the Metropolis algorithm and with the MCMC, the next value, x at time t plus 1, could be the same value x at time t. Okay, so this could happen, and this happens, with a non-zero probability. It happens, a fair amount of time actually. Okay, so I want to just point out a couple things. This function f of x only needs to be proportional to the target distribution p of x. Okay, the exact form of the target density P of X is not needed, okay? That PDF, you don't need the exact form of it. And you just need F of X to be equal to P of X multiplied by some constant C, okay? C has to be a, positive constant, but it's fine if you don't know exactly what it is. Because if you calculate P move as, F of X proposed divided by F of X current, okay, you can see that, well, if F of X is equal to C, some constant times P, the C's will cancel, and it's equivalent to using P of X proposed divided by P current, okay? So using F of X would give you the same result as using the probability, the actual probability distribution, okay? So, so F of X only needs to be proportional to P of X. All right, so why is this a useful thing? Okay, it's very useful in Bayesian statistics, okay? So for Bayesian statistics, we often want to generate values from some posterior distribution, probability of theta given X, right? So we want a posterior distribution of some parameter theta given the value that we saw X. And Bayes' rule says the posterior is equal to the likelihood, X given theta, times the probability of theta, the prior, divided by this marginal probability. The marginal probability is the probability of the data, regardless of the value of theta. Okay, and this marginal probability sometimes is really, really hard to calculate. Okay, sometimes it's very difficult. It's a normalizing constant. It does not depend on theta itself. Okay, it doesn't depend on the on theta. Okay, and the way you calculate this marginal probability is that you can sum or integrate the numerator across all possible values of theta. Okay, so I think that's what we did when we were dealing with like the beta binomial. We said, what's the probability of getting this value, but then we calculated it for all possible values of theta and we summed them up, okay? And so this marginal probability can be found by integrating or summing the numerator across all possible values of theta. Sometimes that's really hard to do. Sometimes it's really hard to do. And so this normalizing constant, sometimes it's a challenge. And so, thankfully, we don't actually have to figure it out, okay? So instead of trying to figure out exactly the exact form of this, we can just use a function that's proportional to it. So we know that f of theta, if I just say f of theta is equal to the numerator, we know that f of theta is going to be proportional to the posterior distribution, okay? And so this saves us a lot of work, okay? Is that we can generate samples from this posterior distribution without actually knowing the exact form of the posterior, because there could be, there could be like millions of possible values of theta, but you just don't know them all. Okay, so that's great. That's a benefit. All right, and let me talk about the proposal distribution. Okay, so for the Metropolis algorithm, the proposal distribution needs to be symmetric. You can have distributions that aren't symmetric as proposal distributions, but then you have to account for that, and that becomes what we call the Metropolis Hastings algorithm. But here are just a few common choices. Some common choices for the Metropolis algorithm is the normal distribution, which is centered at your current value x at time t and has some arbitrary variance or standard deviation sigma. And so we would say x proposed is generated from the normal distribution where mu is equal to your current value x at time t with some arbitrary value sigma. Okay. And if you wanted to do this in R code, you'd say your proposed value comes from the random normal, just one value from the random normal, where mean is equal to x at time t, and the standard deviation is equal to sigma. So that's how you can generate use this proposal distribution in R. Okay. Another proposal distribution is to use a uniform distribution centered at xt with some arbitrary width 2 times C, okay? And so X proposed will come from the uniform distribution where the minimum value is X at time t minus C, and then the upper limit max value is X at time t, the current value plus C, okay? And we can do this in R by doing proposed comes from R unif 1, where min is xt minus C, going up to xt plus C, where the max is xt plus C, right? And so these would generate values from some proposal distribution. And if you think about this, we can see that these are symmetric, that the probability of proposing some value X proposed, if we're currently centered at xt, is the same probability if it's flipped around. If we're centered at X proposed, you know, what's the probability of proposing xt? So if you're at the normal distribution, if you're centered at 0, what's the probability of proposing the value 1? You know, it's some value. And that's the same as if you are centered at 1, you have a normal distribution, what's the probability of proposing the value 0? Okay, those two things would be equal. If you have the uniform distribution, well, the uniform distribution is flat. So if you're centered at one value, what's the probability of proposing this? It's going to be the same as if you're centered over here, and what's the probability of proposing the value over here? So these are symmetric distributions. So this works out here. All right. Is that all right for proposal distributions here? All right, so let's go ahead and try out the Metropolis algorithm. And so let's say our target distribution is the normal distribution centered at 15 with a standard deviation of 3, okay? So the PDF of the normal is this thing. And what I'm gonna do is I'm gonna just to kind of show that I can ignore the normalizing constant, I'm gonna just throw this constant away, okay? And I'm just gonna use the E part. I'm gonna say E to the, you know, -1/2 x minus mu over sigma. So I'm gonna do x minus 15 over 3, quantity squared. That's going to be my f of x. F of x is proportional to the PDF, okay? And for the proposal distribution, I'm going to use a uniform proposal distribution, okay? With a centered at x at time t with a width of 6. So I'm going to go x at time t minus 3, x at time t plus 3. All right, and to illustrate the algorithm's power, I'm going to start with an absolutely terrible location. And we're going to start at 100. The first value is going to be 100. Okay, so we know, you know, if you think about this, right, the target distribution is centered at 15 and has a standard deviation of 3, which means 95% of values are within 2 standard deviations of the mean. So 95% of values are within 15 plus or minus 6. So 95% are between 9 and 21. And then almost 100%, 99.7% of values are going to be between are within 3 standard deviations, so between 6 and 24. So almost 100% are between 6 and 24. So what's the probability I would generate a value like 100? Okay, that probability is practically 0. But just to kind of show how this works, I'm going to start my algorithm at this terrible location 100, and let's just see what happens. Okay, so here's the code. F is a function that's proportional to the target PDF. Okay. So if you recall, like, it's not easy generating random values from the normal distribution, right? I mean, we can do the Box-Mueller transform, and we can do this, you know, Cartesian to coordinate thing, but it takes a little bit of creativity to generate values from the random uniform, but I mean, random normal. But here, you know, here I've got a function that's proportional to the random normal. My proposal function is the uniform distribution. I'm going to generate one value somewhere between current minus 3 and current plus 3. Okay, and then I just run the same Metropolis algorithm. This code is the same as before. We take x at time t as our current value. We propose a value based on our current value. I calculate f at the proposed location, f at the current location to get my p move, and then I either accept or I reject that proposed value based on a random uniform value. Okay, and then here I'm starting off at 100, which is a terrible location. Okay, so I'm going to generate 5,000 samples. All right, so I run this, and this is what my Markov chain looks like. I start off at the location 100. And we can see that, yeah, in the beginning, the chain just keeps generating values, and it moves closer and closer and closer and closer until it finally gets around to where the normal distribution should be generating values. Normal distribution should be generating values around 15 to around 15, somewhere between 9 and 21 most of the time, maybe between 6 and 24. So it should be generating values around there. And we're getting, and it takes a while. Maybe it takes 150, 180 iterations or so to kind of get to that region. But then once it gets to that region, it seems to be generating values. It seems to be generating values according to that normal distribution. Okay, so this. Okay, I'm sorry, we got a question. It says, what does the propose function here propose again? So yeah, what it does, the propose function proposes a value. It proposes the x proposed, okay? It takes your current value, x at time t, and it's gonna generate a value somewhere between 3 above and 3 less. So if your current value is 100, it's gonna propose a value somewhere between 97 and 103, okay? It's random uniform, so maybe it proposes, 97.1. Maybe it proposes, 101. Maybe it proposes 99. Okay, it's going to propose a value between 97 and 103. So it takes your current value, and then it proposes a value between current -3 and current +3. Okay, and it just kind of does that over and over. I mean, it just does that one time, but for every iteration, you're going to propose a new value here. Every iteration, you propose a new value. Okay, so we start off at 100, and it just proposes a whole bunch of values in it, and it keeps moving down. And what we see is that, here, every time, so I drew this. So this is our target area, right? It's a normal distribution centered at 15, and I intentionally started off at this terrible location 100, okay? And so in the beginning, if it proposes anything closer to the mean, like say 97, 98, whatever, it's going to definitely move there, because the probability, if you look at the function, okay, if x is at 100, this numerator is 100 minus 15, it's 85 divided by 3 squared, and it's raised to the negative, right? So this is some number, right? If you propose anything closer to 15, say 97 minus 15, it only has a difference of 82. 82 squared, is going to be smaller. And so, so it's going to have a higher probability because it's raised to the negative that thing. So any values that are proposed that are closer to 15 are going to get accepted. So, so we're going to take steps and keep moving closer to this way. Now, sometimes the proposal distribution will propose values that go in the opposite direction. So it looks like right here I'm at around 90. And when I got to 90, it looks like I proposed values that were farther away. Like I proposed 95 and 93, or something farther away from 15. And those all kind of got rejected, okay? So we didn't accept any of those. So we just keep moving towards the areas where there's higher probabilities. And only until we got around here do we start seeing the line start to move back in the opposite direction, where I proposed a value in the opposite direction, and we said, okay, yeah, maybe I'll accept that value, and we take some steps backwards, okay? And really, once we get to kind of the region of high probability, once we kind of get to this region, then we're comfortable kind of moving this way and that way, moving back and forth. That's what we kind of see here. All right, so anyway, all of these values up here, where I started at the terrible location until I got to kind of this reasonable region, those are what we call the burn-in values, and we're going to throw them away. Okay, we're going to just throw away those first 180 values. We know that those values aren't really representative of the target distribution, that they're just generated because the Markov chain started off at this terrible location. Okay, but this is a really great thing about the Metropolis algorithm or other Markov chains is that you might not know anything about the target distribution. You might say, okay, I've done some math and I know my target distribution has this kind of shape, but I don't actually know the region where there's a high probability. All right, and so you can just give it some really terrible starting conditions and you just let the algorithm run, and the algorithm is going to eventually find its way to an area where there's higher probabilities. Okay, let me give you your second quiz answer. I got too into my train of thought here. Okay, second quiz answer is A. A as an apple. A as an apple is the second quiz answer for today. All right, so that's what's a great thing about the Metropolis algorithms. You can give it poor starting condition. It's going to eventually move to a region where the probabilities are high. Okay, so here are the kind of the values that I've kept, and I look at this and it looks like it fits the normal distribution fairly well. Here's a plot of the empirical CDF versus the theoretic CDF. We don't get perfect alignment, but we get some decent values here. Okay, again, second quiz answer is A. A as an apple. All right, let's talk about efficiency. Okay, now in the ideal scenario, values generated by the chain would resemble random independent draws from the target distribution. Okay, now this is practically impossible. Okay, the whole idea of a Markov chain is that you are not generating independent values, is that the next value depends on your current value, right? Your proposed value, your next proposed value depends on what your current value is. And so it's almost impossible to get a chain where the values are, well, it is impossible to get a Markov chain where the next values are independent, okay? But what we want is that we want it to look like they're almost independent, okay? So this is what just 1,000 IID independent values drawn from the normal distribution look like. So I just used R norm. I said, give me 1,000 values. And this is what IID values look like, okay? There's no correlation. It's just kind of bouncing all over the place. This is the ideal target, okay? This is what would happen if the values are independent. This is what our chain looks like, okay? It bounces around, but it doesn't quite look like this, okay? And that's because our our proposal distribution is always going to propose a value that's either somewhere between 3 above and 3 below my current value, okay? And so we can see, you know, there's definitely some kind of path, and the next value that comes up is related to the current value that I have, okay? And so, you know, when you're doing Markov chain Monte Carlo, you want to try to experiment and try out different proposal distributions and just kind of see the performance of these things. And you want to try messing around with adjusting the variance of your proposal distribution. So just to kind of give you a sense of what happens, I'm going to just try some extreme values, right? I'm going to try a proposal distribution with a width of 100. These are all going to be uniform distributions, okay? I'm going to try one with a width of 1. I'll try one with a width of 12. My current one has a width of 6. We're going plus or minus 3, okay? And then I'm going to start my chains at 15, which is, you know, kind of centered at the target location. So I don't have to worry about throwing away burn-in values, right? So for my initial example, we started off at 100, and we just showed that it'll eventually reach your target location. I'm going to go ahead and just start off at 15, so I don't have to worry about throwing away any burn-in values. Okay, so so here my proposal function is going to take my current value, and it's going to propose a value between current minus 50 and current plus 50. Okay, what do you think is going to happen here? What kind of values will it propose? And will it accept those values that it proposes? All right, so let's just see. I started off at 15, and what we see is these flat regions, okay? And it almost looks like a cityscape, okay, of like skyscrapers and stuff, all right? So let's just take a look at what happened here. Here it looks like I'm around 15 or 16, okay? And if we think about the proposal distribution, it proposes values anywhere from plus or minus 50, okay? From, if I'm centered at 15, it's going to propose values from negative 35 up to positive 65, okay? And so let's say it proposes a value like 60, okay? Is it going to accept a value like 60? No, it's not, because the target distribution basically says values should always be between kind of like 6 and 24. Most of them should be between 9 and 21. So will it ever accept a value like, if it proposes 60, will accept that? No. And basically, we have this flat region because every time it proposes a bad value, it rejects it and it recycles the current value. So the current value that I'm at, maybe 15 or 16, just gets used over and over and over again because I keep proposing really bad values. I'm like, what about 60? No. What about negative 30? No. What about 45? No. What about negative 25? No. Okay. And it just keeps rejecting all of those values until finally I say, all right, what about 14? And it says 14 I can do, and it accepts that. Okay. And so we get these areas where it just kind of keeps proposing a bunch of values and they all get rejected. So you get all of these kind of flat regions where the same value appears multiple times in the chain. Okay, so you don't want this. You're going to want to have to shrink your proposal distribution. Okay, on the other extreme, I'm going to try a proposal distribution where the width is 1. Okay, I'm going to take my current value and I'm going to propose either go up 0.5 or down 0.5. Okay, and so what happens here? Okay, now I get a chain that just kind of goes all over the place. It looks like a random walk. And the issue here is that if my proposal distribution is very narrow, then that means the proposed value is going to be pretty close to the current value, whatever it is. Okay, so whatever my current value is, my proposed value is going to be close to it because my proposal distribution is very narrow. All right, and so if your proposed value is similar in value to your current value, then f at the proposed value is going to be similar in value to f at the current value. Okay? F of x proposed is going to be similar to f of x current. And then p move, which is the ratio between f of x proposed and f of x current, that's going to be fairly close to 1. So that means you're going to kind of accept nearly every proposed value. Every proposed value you generate, nearly every single one of them is going to get accepted. All right, and that's actually not a desirable trait. Okay, is that, you know, the chain is going to move only in small increments, and it's going to kind of look like a random walk. And sometimes your chain can get can drift into regions of low probability and kind of get stuck there. Okay, so having accepting almost every single value is not a desirable thing, and it just kind of means that you're only proposing small incremental shifts, which might not be desirable either. Okay, because remember, the target chain that we want something to look like this. This is what we want it to look like. This is independent. Now that's impossible. That's an impossible standard to achieve. Okay, but we can say, well, this is no good, and this is no good. Okay, so here's something in between where I try a width of say 12. And this is kind of the trace that it looks like. And I would say, you know, this looks decent. Okay, it's not perfect. It's not exactly the same as this, but it looks fairly decent as well. Okay, and that's using a proposal width of around 12 or so. Okay, so you know, proper implementation of Markov chain of Monte Carlo requires experimenting with proposal distributions, and you got to kind of try some of them out. And so these are some ideas here. Okay. Let me give you your last quiz answer. Last quiz answer is E. E as an elephant. E as an elephant is your last quiz answer. Okay. Wednesday is a holiday. Wednesday is Veterans Day. So, you know, we want to thank and recognize and honor the veterans of our military for their service. so we'll have no class on Wednesday, no quiz, no viewing quiz on Wednesday, and we'll see you guys on Friday. Okay, so our next class will be Friday. All right, so we'll see you then. On Friday, we'll look at the Metropolis Hastings algorithm, which is a little bit of a generalization of this with a non-symmetric proposal. All right, we'll see you guys then.